Great. Is my screen visible to all? Does it say upcoming circuit compilation, etc.?
Yes, ma'am. Yes, ma'am. Visible.
Okay, great. So this session will be an introduction to transpilation. Now, transpilation, I would say, is more of an IBM native term, but quantum circuit compilation is universal to quantum computing. It is an absolute necessity if you want to be able to do quantum computing on a real piece of quantum hardware. Why is that the case? When you're building a quantum computer, you're not going to try and put every single gate you can possibly think of, right? And in fact, there are, like, you can come up with infinities of unitaries. So it's not like you can actually, design a computer with every single gate, like a direct, like it like directly supported on it. What is instead done, I mean, this is quite obvious, but what is instead done is that you build a quantum computer with a universal basis gate set. What is a universal basis gate set? With the help of a few different gates, you are somehow able to implement every other possible gate. So if you have a gate that is not in the native basis set, so if you think back about the processes we discussed before, like different chips had different native basis gate sets, right? So what this means is, like especially in terms of 2-qubit gates, you can see the difference. Like Eagle support ECR, Heron support CZ, and Falcon supported CX, which is nothing but C naught. So, like, since given that this is differing across different, generations of hardware, you have to realize that, the way you do the quantum circuit compilation, basically you take a virtual circuit, you make it ready for being implemented. Forget doing it well. To be able to do it itself, you need to first break down certain things and, first decompose your virtual circuit in terms of gates that can be supported natively on the back end you're implementing it on. So transpilation or quantum circuit compilation. So it's called transpilation because it's translation plus compilation. Translation meaning that you translate your, I mean, we say translate, but it's basically you decompose, or you translate the gates of the circuit you have to the gates that the computer can support. So that is the translation part, and the compilation part is you want to make that efficient. You want to make that doable on a quantum computer, you want to make that efficient on a quantum computer, and you want to you we will discuss what are the hardware constraints. But of course, just putting something on directly on a quantum computer is not going to be that easy. And one of the things that we discussed before, say you have two very distant qubits and you want to put a 2-qubit gate between them, how do you possibly do it? So this is, for example, a hardware constraint. So how do you deal with all of these problems? So the basically dealing with all of these problems is to transpile your circuit or do quantum circuit compilation on it. And it's something that you do very much in the context of a hardware. Of course, you can do it without the context of hardware. How? I hope this is not confusing, but so transpilation is many things. You make it implementable on hardware, you make it efficiently implementable on hardware. Basically, you reduce the depth. You can do several things, right? So, like when we look at the stages, we'll understand a bit more. But compilation is a multi sort of step process. And what are all involved in this process? So, okay, before that, let us understand what is quantum circuit compilation. You take an abstract or virtual quantum circuit and output an optimized physical circuit. Now, this is the most compact and complete description of what is quantum circuit compilation. Why? You take an abstract or virtual quantum circuit and output an optimized, which means you want to convert your gates into as efficient set of gates as possible. And it has to be a physical circuit. What is a physical circuit? A circuit that can be implemented on hardware is called a physical circuit. Why is it necessary? You have hardware constraints. What are hardware constraints? Say you have two very distant qubits, but you want to implement a CNOT gate between them. How do you implement that? So that is one question. Say you have a 10 qubit circuit, 10 qubit circuit that you want to implement on a 50 qubit backend. Okay. And in this 50 qubit backend, you know that some few different qubits are extremely noisy. So when you implement this 10 qubit circuit, you will have better luck with getting a good answer or less noisy answer if you avoid those noisy qubits and implement your circuit on good quality qubits. So, if you look at the compute resources page in the IBM Quantum platform, you'll see that there is always a section, or if you just look at the coupling map, actually, the ones which are sort of dark are high fidelity. The ones which are light or very light purple, if you hover over each different qubits, right, you'll see that the different nodes of the graph coupling map which you see, those are all differently colored. The reason is the noise on individual qubits is not going to be the same throughout the entire day, even like forget throughout the month or throughout the week. It's going to change often. And to make sure that we know what is the status of each qubit, like we calibrate the qubits. So this calibration comes in form of readout error data and gate fidelities. So from this data you can infer what are qubits which don't support high fidelity sort of 2 qubit gates across them, which are good quality qubits. So these are all some hardware constraints to keep in mind. And aside from that, sometimes you have to, like, your gate, the circuit you're coming up with will have too many gates. So in terms of having too many gates, the main constraint comes in terms of gate depth. So it's okay if you have say 50, say if you have 50 gates on each of the qubit, okay, but you only have say 3 4 layers of them, you can still implement that. It may still be implementable without much difficulty, because each of the operations act on individual qubits, and it's not going to be difficult to implement all those 50 simultaneously. However, say if you have 50 layers of c naught gates one after the other which are linearly connected, meaning that I have one between 0 1 1 2 2 3 3 4 and so on. Say I have 3 layers of that becomes a more difficult one to implement, because when I'm implementing 0 and the gate between 0 and 1, I cannot implement the gate between 1 and 2, and so on, right? Because when if I'm implementing that, it's going to interfere with the state that is on the first qubit, right? So that is the so if you want to understand more about gate depth, it's that kind of a quantity. So the gate depth of the second circuit I described is much higher. So okay, now giving more context in the terms of the algorithms that you might have discussed so far, the reason why it's difficult to implement Shor's algorithm, Grover's algorithm, Grover less so, definitely more Shor, but also the other fundamental quantum algorithms, right? Like quantum phase estimation. If you look at the gate depth that is incurred by these, even for small problems, it's huge. So when you have to implement these problems on real hardware, it's going to be difficult, because the problems, the circuits have way too much depth than what can be supported by the backends. However, say I compile my circuit in a way A, in a specific way A versus a specific way B. If I am somehow able to compile it in a more efficient manner B, such that it has less depth, then I definitely want to implement the way through B rather than A, because the lesser gate depth circuit is first of all more implementable, but it's also less affected by noise somehow. Okay, this is a bit of a generic statement. I wouldn't say, I would say that it's not generally applicable. It is something that I'm qualitatively saying. So you need to really think about specific cases, but gate in terms of gate depth, you want to implement circuits which have less gate depth. And the other thing is, unoptimized circuits are more affected by noise than unoptimized circuits. Why? Because the more gates you have, the more noise those gates the more noise that comes across the computation while applying those gates, and that finally leads to low fidelity outcomes. So let's first look at the first constraint, which is the hardware constraint, and also we will discuss the others. Okay, But first, hardware constraints. So let us take this circuit for example. Okay, I have, what is this? This is a very randomly constructed circuit. I have a Hadamard, I have three C knots, which up to here it usually looks like your typical 4-qubit GHZ circuit. But I also have an X gate here and I have a ZZ gate here. And it's an RZZ, so it's RZZ of pi on 3 and 4. So this is the way you would write this quantum circuit in Qiskit, right? Now, this is the circuit I have. But if I want to actually implement this circuit on different backends, these are the different circuits that I'll get. Now, if you just take one look, you can see that they look vastly different, right? They're not at all similar. But all these are the same circuit. If you start, like you start with something here and you measure whatever here, you will get the same result. Ideally, you do this, say this part of the thing on a simulator and you do this on different backends, these will all technically should yield you the same answer. However, just look at, however, you will not ideally observe that, but because just look at the way these, like the gates have been decomposed, right? You have some ECRs here, you have some C naughts here, RZ, square root of X, and you also see some Q4 going to 3, Q3 going to 5, Q0 going to 8, and here you see Q4 going to 56, Q3 going to 57. So now this should hint to some of you at least what is happening here. I said these have been transpiled across different or compiled across different backends. So which of the different backends are these? So this first one has been compiled on IBM Hanoi, which is I think 27 qubits. So on a 27 qubit backend, which supports RZ gates, C0 gates, square root of X and X gates, this is what the circuit looks like. On IBM Brisbane with a specific layout, if I say I want 58, in this case, in this case, the transpiled circuit basically worked in such a way that the fourth qubit in your virtual circuit, so basically Q4 here, has been mapped to the third qubit on your hardware. Basically, the third qubit in IBM Hanoi has been is mapped to the fourth qubit from your virtual circuit, and the zeroth qubit corresponds to the eighth qubit. Third one, Q3 in your virtual circuit corresponds to 5, Q2 to 9, and Q1 to 11. And this part, the Hadamard, the C naught, the square root of RZZ, if you see the square root of RZZ has been decomposed here because you no longer have it in this, right? However, IBM Hanoi native gates, it supports all these. It supports C naught, it supports X, RZ square root of X, and yeah, it supports these gates. So now it has been decomposed to these following. So here again, when I transpiled it on IBM Brisbane, it taught sometimes it, so this is something called as a trivial layout. So in this case, what I've done is I have mapped the 0th qubit to the 0th qubit of Brisbane, first qubit to first qubit of virtual circuit to first qubit of Brisbane, 2 to 2, 3 to 3, and so on. So if you see, look at how much more depth this particular circuit has compared to this circuit. Now, why is that the case? The reason, I mean, I don't have the coupling map of Brisbane here, but this happens because so this is called as a trivial layout. If you want to map 0 to 0, 1 to 1, it's called a trivial layout. Okay. And this particular part, the way the virtual qubit is mapped to the physical qubit, this is called as layout. Or this is the layout information. Specifically mapping itself, it is called as routing. So usually in the context of transpilation, there are several stages. We will discuss them one by one. But this layout and routing, they are generally discussed together. And here what has happened is, in one case it's a trivial layout, but it's a very inefficient circuit. Here it is a non-trivial layout where the fourth has gone to 56, third has gone to 57, 0 has gone to 58, and so on. But you have a much more optimized low depth circuit here with much lesser 2 qubit gates. Just compare how many less are there. You have here 1, 2, 3, 4, 5 2 qubit gates, whereas here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 2 qubit gates. And of course, there are more single qubit gates as well. But this is just comparing two different circuits on IBM Brisbane only, but with different layouts. And if I transpile this on IBM Fez, you see that 1 goes to 2, 0 goes to 3, 3 goes to 4, and so on, right? So and also notice the gates here. Here you had C naught for 2 qubit. Here you have ECR, which means that, I mean, of course, this is true. IBM Brisbane is an Eagle backend, so you have ECR gates, and you have square root of X, RZ. Here also RZZ gate got decomposed. So then here in transpiled on IBM Fez, which is a Heron backend, you have CZ gates, and you see that the circuit is also like lower in depth. So this is just to show you, I mean, like there are hardware constraints, but how different does a circuit look when it's actually being run on a quantum computer compared to when you started? So that is just to show these. And how did I get that? Like I used it to obtain these circuits, I used the preset pass manager only. We will discuss how to use that in like upcoming um, we will discuss that. The second constraint which we discussed, so the hardware, this is also part of the hardware constraint. Some gates between qubits so you will sometimes have to implement gates between qubits which do not have connectivity at the hardware level if you use a trivial mapping, right? So so say I'm just building a 3 qubit quantum circuit, and I say I want to implement it between 0 and 2. Okay. So, so if you look at these two circuits, these are actually equivalent. The reason why I'm showing this is because the solution to this particular problems is to apply as many swap gates as needed to move qubit states back and forth and implement the operation and revert the state back. But you have to realize that it's expensive to do so. Okay. So if you just look at one swap gate, here we transpiled and we sort of broke down the different gates across different types of backends here. Now let's just do that for one swap gate. So if you look at like on Falcon, you have three C0 gates. One swap gate is equivalent to three C0 gates, and it's equivalent to these many gates on Heron, and in turn it is equal to these many gates on Eagle. So if I have to say implement a 2 qubit gate that or a 2 qubit gate that does not like between qubits which do not have connectivity at the hardware level, I'll have to apply swap gates to do this particular operation. Now I'm saying this move back and forth in a generic way. You may not always have to move back and forth if you have multiple like 2 qubit gates. Then there might be a better way to do it. This is just to sort of give a visual representation, okay, or just for understanding sake of like what is actually going on. So this again so this is something that also kind of is taken care of during routing. So during layout you kind of choose, you know, a mapping for a qubit, you try to do it well, but then during routing what you do is you apply swap gates to between qubits where you have to apply a 2 qubit gate but there's no connectivity at the hardware level. So, okay, what is transpilation overall? First, let us discuss that. I didn't go to that in the first slide because I first want to share the challenges or why circuit compilation is really necessary. What are the difficulties associated with doing that before to give some intuition and motivation as to why each of these stages are necessary. Okay. So there are 6 fundamental stages in Qiskit's pre-built transpiler pipeline. Okay. So the first one is init, where any initial passes that are required. Okay, now before discussing this particular slide, I will discuss some key concepts. I'm not going to show like anything specific for these, but I'm going to describe them as simply as I can. Okay, so the first is a coupling map. Okay. Or let us start with backend because that's more simple. So a backend is any quantum device, okay, that is represented on the level of Qiskit. So what does this backend object have? It has properties like properties of the backend associated with it. things like what is the coupling map. What is the coupling map? Which it depicts how different qubits are connected in the backend itself. Then you have things like properties of individual qubits. What is the noise looking like in the overall this thing? What is the configuration looking like? What are the number of qubits on the backend? Basically all properties of the backend or the QPU that is represented on the or accessible to you through the software stack using Qiskit through the backend object. Then you have something called as a target, which is specific, which is an interface, let us say, to between the transpilation routine and the backend. So backend is generally existing, but to specifically transpile on a particular backend, we need an interface, right, to for the circuit to talk back and forth. So that is called as a target. Okay. So when we do quantum circuit compilation, we basically compile the circuit onto a target corresponding to a backend based on the coupling map. I hope that sentence makes sense. Please ask me if it's not clear. I'm happy to explain again. Okay. Now, even before that, right? What is a DAG? So I said the circuit has to talk back and forth to the target to go through the transpilation process. Now, coming as such as a set of qubits, some set of gates. How how do you actually systematically implement one gate after the other, or how do you figure it out? I will repeat it once again. I will explain DAG and then I will try to go through it. Okay. So we first transform, we take any, so let us go back to this circuit. Okay. We take this circuit, and we transform it into a structure called as a DAG structure. A DAG is a directed acyclic graph. Okay. So what we do is we represent this whole operation in terms of a graph, a directed acyclic graph. Basically, you start from specific points and then the data flows from the input or the beginning source nodes towards the end nodes, which will be like you finishing the computation on all the input qubits and getting outputs in terms of the quantum. Say you are starting with, okay, this is a quantum circuit. A quantum circuit consists of a quantum register and a classical register. So you will have nodes corresponding to these qubits and the classical registers you're starting with, which will be empty, of course, because you're just initializing the quantum state. So after doing the Hadamard, all these gates, and then say you have some measurements here. Then after the measurements are done, the information from your Q0 will flow to your C0, which is the classical register, right? Now, this will be the case for all qubits. Now, this is something you can represent graphically, but it's very useful to do graphically because you can see a sequence, or you can specify a time, or you can have a sense of when each thing is happening. Say if two events are completely independent, right? Let's go back to this circuit. Okay, so the first three gates, if you see, these are so if you look at this for this C naught, it's between 0 and 1. This is between 0 and 2. This is between 0 and 3. So I cannot simultaneously apply these three gates because it's all interfering. Hello, am I not audible? Am I not audible?
You're audible, ma'am.
Okay. So
Others who have a problem, please check.
okay.
Please
Okay.
go ahead.
Okay, great. So I cannot simultaneously apply these three C0 gates because these are all happening on the 0th qubit, right? However, if you look at this Hadamard, this X gate, these two I can implement simultaneously because this is on the 0th qubit, this is on the 4th qubit. And see, these are some kind of things which can be more intuitively understood or computed by processing it as a graph. Okay, so the reason you convert a quantum circuit to a DAG object is because it is easy to schedule each of these operations one by one, or to look at how each of them is being processed separately. uh, okay, that is just, I mean, this is not a very involved explanation, but it is to give you an idea, qualitative idea as to what is happening here. Okay, so now you have a DAG, which is a directed acyclic graph, and it tells you what are all the operations that need to happen. Right. So, okay. So if you go back here on this, so you have a C naught on 0 and 1. So if I have a node which is corresponding to this particular C naught gate, I will say, for example, have an arrow from both Q0 and Q1, because this is a C naught, this is a 2-qubit gate. For Hadamard, I will only have an arrow from Q0. Okay. So say if I want to kind of, like say during my transpilation process, I want to do something related to this thing, where this part where I'm trying to see whether I need a swap or not in order to implement a C naught between this 0 and 1. Okay, I don't know if these two are connected or not. I have to check with the coupling graph, coupling map of the backend. So that is something you can compare, right? You can first say, does the C naught have two incoming nodes, or two incoming, like does it have two incoming edges? Then it's a 2-qubit gate. So things like this, it's easy to understand this through a DAG, right? So now coming back to what I wanted to repeat, let me put it like this. So you have a quantum circuit, or you have a virtual quantum circuit. First, you convert that into a DAG, or a directed acyclic graph. And while doing quantum circuit compilation, you compile the quantum circuit for a particular backend, which is the quantum device represented on Qiskit, uh, to a specific target based on the coupling map. Okay. So the coupling map is the way the qubits are connected in the backend. The target could be something like, it's a layer of abstraction for the transpilation process itself to work on. Okay. Now, what do I mean by that? Now, I take this DAG. Okay. Now, if while compiling it, I'm going to make changes one by one. I'm not going to do it all at once. Okay. Say, for example, I take this circuit as a DAG, and I want to like say break down this Hadamard gate, because Hadamard gate is not on any of these backends. I know from this backend object, I can look at the native basis gates, and because Hadamard is not there, say I'm doing it for a Falcon. Now, if you look at it, you will understand. So for Falcon, Hadamard is not supported, but C naught is supported. So while in the first step, I can leave the C naughts alone, because this can be implemented on the hardware. But when I'm doing it for, say, like Brisbane, which is a Eagle backend, I cannot leave the C naught alone, because I can only implement an ECR. So here I will not leave the C naught also alone. Same case for IBM FES, which is a Heron backend. So now when I want to modify this Hadamard, like say, okay, I'm not just going to modify Hadamard at once. What I will do is, if there is a unsupported gate in my quantum circuit, based on what is in the native basis gate set of the backend, I hope that's making sense. What I mean is, Hadamard is not apply. I want to now apply all these gates. Just trivially, I want to be able to apply them on the backend. Okay. Now, but Hadamard I cannot apply directly. Say I'm taking the example of a Eagle backend. Hadamard I cannot apply. I cannot apply C naught, any of the C naughts. I cannot apply RZZ either, and I cannot apply X either. So now what I have to do is, I have to decompose each of these gates in terms of what is in the basis gate set of the quantum computer. So I will look at what gates are needed in order to decompose Hadamard into the gates available which were there in Eagle. And this, let us go all the way back here. So we know that the native gate and operations that are enabled are ECR, identity, delay, measure, reset, RZ, SX, X, if else and for loop, if else, for loop and switch case. So coming back here, actually X is supported on the back end, but we don't have an X here. Now why, I can explain, but let me first go step by step. So I will decompose all of these. So this is something that can happen in one stage, right? So I just decompose all the gates which are not supported on a backend in terms of gates that can be supported on a backend. So this is called as a pass. So pass is a basic unit of change that is affected by the transpiler onto the DAG. Okay, so a pass acts on a DAG and it transforms the DAG. And in Qiskit, there are two main kinds of passes. You have a transformation pass and you have an analysis pass. A transformation pass basically it transforms it takes input as the DAG and it transforms your DAG. Whereas the analysis pass, it looks at the property set of a DAG. So a DAG has something associated with it called a property set, which just describes the properties of the DAG or the directed acyclic graph. How many 2-qubit gates are there? How many single qubit gates are there? I said, right, you can kind of infer this information. Which of them have two nodes incoming? If how many nodes have two edges incoming? So that will correspond to the number of 2-qubit gates. So this kind of information will be in the property set, and an analysis pass will mutate this object. Okay, so there are just two kinds of passes which are fundamental to Qiskit, but it's a unit of change on the DAG in some form. Okay, and what is a pass manager? A pass manager executes a set of passes. Okay, so say I want to execute 3 to 4 different passes, I can use the pass manager to implement 1, 2, 3, 4 passes. A staged pass manager is saying that, like defining a function which will execute a set of passes in a specific order or something like that. So you can think of this like pass is an individual musician, a pass manager is like the orchestra, whereas the staged pass manager is the conductor of the orchestra. So that's you can think of it that way. And in transpiler stages, you can implement a specific stage manager which executes different stages of the transpiler. Now let us come back to this. Okay, so you have init. So what are the 6 fundamental stages? You start with a single circuit. You have the init stage where any initial passes that are required before the circuit can be embedded. So before you embed this thing on a circuit, you first need to be able to apply the gates, right? So in the first stage, the thing you will do is even before decomposing it into the basis gates, you will so that is called as translation. But even before doing that, the first thing you should do is unroll gates which have more than 3 qubits. So here I have only 2 qubit gates, right? But if I had a 3 qubit gate, say I had a CCX gate, a CCX gate will in no way be it will be possible to implement on a, because we don't have QPUs that support 3 qubit gate operations as of now. So the first thing you should do is unroll any 3 qubit or multi qubit gates that you might have in your um, in your circuit. So you first decompose those. Then what would you do? Then you will do another set of, in the init stage, you basically initialize the things you need to do in order to embed the circuit itself. So this typically involves unrolling custom instructions and converting the circuit to all single and two qubit gates. Right, so if you have any multi-qubit gates, it will first convert it into single and 2 qubit gates. Okay, then you have layout, which applies a layout mapping the virtual qubits in your circuit to the QPU's physical qubits. So now if you look at this, you see that Q4 is mapped to 3, Q3 is mapped to 5, and so on, right? So this is called as the layout. So in the layout stage, you come up with a mapping for which qubit should be mapped to which. And in routing, once you have a layout which has been set and applied, this will inject swap gates in the original circuit to make it compatible with the QPU's connectivity. So once you apply a layout, you know where the connections between the qubits exist, where it doesn't exist. So if there is an impossible to apply 2 qubit gate, then you will have to add enough swaps such that until you're able to apply that 2 qubit gate. So that is what happens in routing. The reason we go for layout and routing together is also because choosing a good layout means you might need lesser swaps also, right? So like the very first thing we discussed, if you look at this example itself, if I choose a trivial layout here, I have way more 2 qubit gates than if I choose a good layout. So you will need lesser swaps as well. So that's why often layout and routing are sort of clubbed together. Then you have the translation stage where you translate the gates in the circuit to the QPU's basis set of instructions. Then, so this is where you basically take each gate and then decompose it in such a way that it can actually run on the quantum computer. Then you have optimization, which runs an optimization loop to find more efficient decomposition of the quantum circuit until a condition is met, such as a fixed depth. Now here I said that one swap gate is equivalent to 3 C0 gates like this. Okay. Here you have one C0 between 0 and 1, then you have a C0 between 1 and 0, and then you have another C0 between 0 and 1. But suppose say I had somehow in my circuit something came up and I have a C0 between 0 and 1 and then another C0 again between a 0 and 1. So if you look at that effective operation, what is it? It's equivalent to identity. It does nothing basically. So it's like a redundant operation. Same if you have two x's one after the other, an x gate and then another x gate, that is equivalent to identity, right? So you can also have combinations of gates, say some 5 6 gates together, which is equivalent to a single unitary, right? So in these cases it will be more optimal to implement a single gate or a single 2 qubit gate than implement a bunch of them together, right? So in the optimization stage, you kind of try to find chunks of gates which are one after the other, which can be condensed to a single gate. So that happens during the optimization stage. And finally, during scheduling, it's for any hardware aware, scheduling. So, like us in okay, so you cannot simultaneously do operations on multiple qubits at once. Okay, it can disturb the whole quantum state and it can lead to issues. So a lot of times it's like there is a specific way that the operations on each qubit are going to happen. So if you want to schedule these things, say for example you want to say that schedule a specific gate as late as possible, or schedule a gate as early as possible or as soon as possible. So these are some kind of things also which you can supply to the supply to the compilation routine. And it's even more when you come to like say things like dynamical decoupling, these things become more relevant, because dynamical decoupling during and the idle time of a qubit, or during the idle time of a qubit, is good to stabilize it. But if you want to like apply dynamical decoupling, you want to know how it is being, how the operations are scheduled, to know when the idle time is coming up, right? So this is again a qualitative explanation, there's more to this. But scheduling is for this last stage is for hardware aware scheduling passes. Okay, so this is an overview of all the 6 stages that you have in the transpilation routine, and these are some of the important concepts to understand in terms of what comprises a transpilation, comprises transpilation. So now I would like to move to a notebook. But yeah, like I'll very quickly just show something simple on how you can do transpilation, or how you can just try to like play with a few factors and see what. Okay, an important thing to understand: if you don't set this parameter called as a seed transpiler, or like a transpiler seed, every time you do a transpilation process, every time basically you transpile a circuit like here, you will get a different result. It could be a different layout, it could be a different set of decomposition, but it's extremely important to understand that transpilation is a stochastic process. Unless you specify a transpiler seed, in which case you will be able to reproduce the same transpilation you did like in a specific at a previous step or a previous trial, you will get different answers. You may get the same one, but it is most likely a coincidence, right? So unless you set a transpiler seed, transpilation is a stochastic process, and it's good to keep that in mind. Okay, so in terms of general good practices, while say you are doing benchmarking or you are conducting experiments, it's good to use a transpiler seed in general. It's not an absolute necessity, but it's a good practice to be able to keep track of things and to be able to reproduce your results. Okay. In terms of that, so like I will show how you can, use different optimization levels using like a pre-made pass manager which exists in Qiskit. And yeah, you can transpile circuit and see. I'll stop sharing and I'll move to the notebook now. Is this visible? Okay. So, okay. So there is this object called as a generate preset pass manager in Qiskit. Okay. And you can use this at different optimization levels to get highly optimized circuits, but they will take a little bit more time. Or you can just do some very basic transpilation to make your circuit barely implementable on a quantum computer. Okay. So real quantum devices are subject to noise and gate errors. So you have to transpile them in order to reduce their gate count and depth. And this can make your results better as well. Okay. So this generate preset pass manager basically it takes two main arguments. One is the backend because you have to compile against a specific backend, and the optimization level, which kind of controls how much you how heavily you want to compile your circuit. So if you set optimization level to be 0, this doesn't really do any optimization, but it does basic translation, which means it converts all the gates to the native gate basis set of your hardware which you are implementing on, and it does layout and routing where it selects some kind of it does a trivial layout. Okay. Where it selects the same physical qubit numbers as virtual and inserts swaps to make it work. Okay. Then at optimization level, you have light optimization. So here the layout and routing, this is going to, okay. So what is this trivial layout and basis translation, and these are all passes, right? I mentioned that passes are units of change to the DAG. So you can come up with several passes, and there are several passes which exist in Qiskit, which does different specific changes corresponding to different stages of the transpilation routine. Okay. So this, I'm not going to go in depth into this. You can like refer back to the documentation. This is from the documentation only. So you can refer back to this. But essentially, at different steps you have different passes are going to do different things. So for example, inverse cancellation is if you have a unitary and you have an inverse of the unitary right next to it, then those two are going to effectively be removed because they are doing only an identity operation. So yeah, so like you can see the extra passes that are added or what are the extra steps that are done in order to go from no optimization to high optimization. So let us implement this. This is just some unitary gate and this is a random unitary along with a swap. Okay. And fake Sherbrooke is used as a mock backend in this example. So let us first compile this using optimization level 0. Now let me do one thing. This is given site transpiler is 1, 2, 3, 4, 5, right? I'm going to remove this and let us see what it gives. It's giving the same thing. Okay. Sometimes it differs, sometimes it's the same, because here right now, if you see, it's actually optimization level 0, right? So here it's coming out to be the same, but I'm sure we will observe something different for optimization level 1. So let us see. So if you see, this has 6 ECR gates, right? And several single qubit gates. Now what happens at optimization level 1? Now, if you, okay, I've already spoiled this up, like sort of suspense if there was any, because I've already printed the circuit. But yeah, see, if you see here, it is 1, 2, 3, 4, okay, 6 here also. But you have lesser single qubit gates, right? Clearly, the depth is different here than there. But let us do this. Let us see if we are observing a significant difference. Okay, not much difference here, but that's okay. See, like in 2 qubit, like here, this is a 2 qubit circuit, and okay, it's decomposing a single unitary, right? So that is probably why you are not seeing much difference. But I leave this to you as an exercise. Please try it out. Like take a random circuit and try compiling it across different compiling it at different optimization levels without giving a transpiler seed, right? Okay, here we have some layout. This here 0 is mapped to 60 and 1 is mapped to 61. So here we were able to reproduce it if we use a seed transpiler. However, if we don't, let us see what happens. Okay, should I delete this and check in case it's not being... It's also picking the most optimal sort of mapping, right? So that could also be a reason why it's not getting changed. All right. But yeah, if you see again, this is for optimization level 3. If you see here for the second optimization level 2 and 3, it's almost looking the same, right? I would attribute that to this being a very simple unitary. I don't know. I don't have much time, but okay, let's very simply, okay, it will take a bit more time. You can do this as an exercise. Like you can, okay, these some of these are other. So approximation degree is another sort of parameter where you say I want it to go to this extent, like push the optimization procedure until this extent that I get lesser like depth circuit. So then you get this sort of thing. You can explore the different parameters from the API docs. So if we hover over this, it's a heuristic dial used for circuit approximation. So 0.99 means you want to produce a circuit which is very close or almost exactly the same as the unitary and the swap that you started with. So that is giving us something with much lower depth, right? And this is just some way to kind of quantify the instruction. So I'm going to skip that. Okay, it's almost 4:14. I'm already 15 minutes over time, so probably I think I should do can we take maybe like 5 more minutes? Would that be possible?
Yes, ma'am. Please go ahead. No problem.
Okay, then let's just do this circuit, like very simple one, but not trivial like this unitary. Okay, I don't want a random U. I will increase this to 4 and then going to say QC dot H of 0. Let's put a Hadamard. Then QC dot CX of 0, 1. Let me put QC dot say RZZ of 3.14 or yeah, let it be 3.14, 2 and 1 dot Y of say 4. Yeah. Oh no, it should be only up to 3. I'm going to put 3 and then I'm going to do QC of SX of... I'm really just putting random things here. So let us see. So this is a pretty random looking circuit, right? So let's implement one 3-qubit gate also, CCX. So you have, let's say 3, 1 and 0. So the target is going to be 0. So this is a 3-qubit gate, right? So now let us transpile this at optimization level 0 on the backend. So I'm also going to put scale to be equal to 0.5. This will make the image a bit smaller because I think this will be decomposed heavily. Let us see what this looks like. Okay, so you see how big this is, right? And here it's a trivial layout. For optimization level 0, you're not going to see much. But you can also just, to be able to check what is the depth of the circuit. Here you can say, look at the depth. So this depth of this circuit is 152. Now let us remove the seed and see if it changes. Okay, it didn't change. But so let us move on to a higher this thing. So for optimization level 1, now what happens? Okay, now I'm going to reinitiate QC. Okay, we have already Yep, okay. So let us run this again. I'm going to do it in the first go itself without the seed. So see here, 2 is mapped to 122, 1 is mapped to 123, 0 to 124, and 3 to 125. Okay. So this is 58. But why are everything... Okay. So this is 58. Suppose I do this again. Okay. It's a bit anticlimactic. But I assure you this does change for other cases. Okay. So now with the C transpiler, I see this. You can see the layout is this. QC dot underscore T2 underscore exact dot depth. So this is 48. Suppose I remove the C transpiler and I check the depth. Okay, finally we have a change. So it went from 48 to 46. Okay. Now let us just run this again and see. It is saying the same, but ultimately the optimization it needs to do is kind of similar, right? So you can expect it to change a bit, but it changes. See, it does change. Like it's not a repetitive process every single time. So the layout may change, the depth may change. You may have some different, like gates here. Of course, it will be similar to some extent because it has to ultimately yield the same circuit. But you may observe some changes here and there, is my point. So the reason it is mapping to these qubits is likely because based on the noise profile, the connectivity and everything, this gives the most efficient result. So let's go T3, let's go exact dot depth. Okay, this is for the given seed, which is 1, 2, 3, 4, 5. Now even without the seed, it's giving 48, right? So certain times it happens that a more heavily optimized circuit might have more depth than like for a lower depth. So it is usually a good practice to try to um, transpile over few different parameters and just take the one with the minimum depth because that makes it better when you're trying to run it on the back end. So let us try for this. You see, so this is the approx one depth. So here you're seeing more of a reduction in the depth. Suppose we remove the C transpiler. See, it's changing. It's gone down from 39 to 34. So something has changed in the circuit. So if you have more time and you're doing it like while you're by yourself, you can see how these parameters change. Okay. So yeah, with this, I would like to close the session. I've thankfully taken only exactly 5 more minutes. So I'll stop sharing. Do you have any questions? Okay, how to construct an oracle? Like you mean oracle, if you're talking about the Grover algorithm in specific, like, I mean, one of the biggest challenges. So you can come up with a sort of theoretical way to say how you want to, create an oracle, but it really is the challenge when it comes to solving a practical problem. So if you want to implement Grover for a practical problem, you have to think about how to construct the oracle for that problem. So, the mapping from like the problem to a quantum circuit, that's where the complexity comes in. It's not something that you can answer generically, but if you explore the literature, you will find some papers which give you a good way to do that. So yeah, I would recommend you to look into the literature. Is there any other question? I don't really say. I don't really have a answer for that question. Like, can we say the ultimate achievable reduction in depth is limited by the Solvay-Kitaev theorem? I cannot, off the top of my head, I cannot answer that question. Maybe I can get back to you on that. Thank you, everyone. Okay, Shore's, is it possible to implement Shore's algorithm on in Qiskit simulator? You can try to solve something like of low complexity, like something very simple you can try to do. But Shore's algorithm is on something that can run on fault tolerant quantum computers. It needs fault tolerant quantum computers. It's definitely not in the scope of a quantum simulator. It will be very challenging. So the answer is actually no. I would say no. Like you can implement maybe just a simple sort of trivial case. You can sort of come up with a way to write it. But if you want to practically use Shore on a simulator to say factorize a 3-digit, 4-digit number, it's just not possible. I think can we close the session? Thank you everyone for your attention.
Yeah. Thank you, ma'am. Thank you for your time and thank you for joining this session. And you can see the excitement. People are still there with you till the end of the session. So yeah, last time also, whenever Janani ma'am has taken a lot of information and so thank you for the passion with which you deliver the lecture. And please share the slides and the questions for that quiz. Yeah. Thank you so much, ma'am, for joining, and thank you all participants to be there. And yeah, you can share your appreciation for Janani ma'am, and we will conclude here. The exam is open, quiz is open. Please take the quiz today and tomorrow, and on Sunday till Sunday midnight. Please take the quiz and continue. And thank you all. Thank you, ma'am. Thank you
Thank
for
you
being there.
everyone
Yeah.
for your attention, and thank you Pili sir and everyone else for EICT and MNIT Jaipur. Thank you for conducting this session. Thank you everyone.
Yes. Thank you.
Yeah, bye.
Yes, ma'am. Bye. Yeah. Thank you all.
Yeah. Thank you all.